All right, guys, good morning. We're going to talk about hydrates today. The first question that will come to your mind is, what is a hydrate? So a hydrate is a subcategory. Do we need a second to get notes out and be ready? All right, let's take a moment. All right, so we got those notes out. We are ready to go. A hydrate is actually a subcategory of ionic compounds. Remember that an ionic compound is one that's a metal and a non-metal, and they group together in kind of a lattice, in kind of a well-organized stacking of molecules. All right. And what happens with hydrates is water molecules become wedged into the lattice work. All right. And so in the case of a hydrate, there are some water molecules that become trapped or fixed, within the lattice, within the ionic lattice. They are not bonded, so they are not actually a part of the chemical structure, but they are trapped within the ionic lattice.
What's that? Oh, lattice.
So the lattice is the organization. Let me just show you kind of a picture. Like if maybe we have NaCl. Let's see. In the case of NaCl, I'm going to draw this wrong. We're just going to be okay with it. And then you've got some other smaller molecules that would be like the Cls. And then you've got your NAs. And then you've got your Cls. And so the lattice is this structured organization and stacking of the sodiums and the chlorines, or the whatever and the whatever. All right, does that make sense? Okay, no? Did I hear a no? Okay. So the lattice is just, I want you to imagine that you have like some tennis balls and some golf balls, and you lay out the tennis balls and stack the golf balls on them, and then put another layer of tennis balls and another layer of golf balls. We would call that a lattice. And that's the way that ionic compounds actually group together in structure. Okay, is like a stack of those different kinds of tennis balls and golf balls. And so as you stack those together, it forms this nice organized crystal. And what happens then is waters. Oops, we weren't going to do red. Oh no, let's try red and see if it. Waters end up getting wedged in there. Okay. There we go. Is it drawing in there pretty well? Yeah. And so what happens is the waters get wedged in there. They do not bond. They just get trapped and wedged into that organization, into that little stacking crystal. All right. So let's see. So I'm going to say that they are not bonded. They are not bonded. Okay. But they are present usually in a fixed ratio. All right. And so we've got those water molecules. And they are there, and they are in a fixed ratio. And so the way that we would name that, okay, you would write the name of the ionic compound, and then you put a dot, and then you put a numeric prefix and the word hydrate. All right, so that all sounds a little bit weird, but let's just say, just for fun, that you had some magnesium sulfate. Okay, so let's say that we've got our magnesium. Let's say that this is magnesium sulfate. All right. Let's see. So I'm going to say, hey, look, I've got some magnesium sulfate up here. And the magnesiums would be like the little blues, and the sulfates would be like the big greens. All right. And they would be stacked in there in a nice organized way. And then I've got my little red water molecules stacked in there. Here's the thing. For every molecule of MgSO4, there are actually 7 water molecules wedged into the crystal structure. And so we would call that magnesium sulfate. Does anyone remember the numerical prefix for 7? Hepta. All right, and I squeezed it in there because I was running out of space at the end. So I've got magnesium sulfate heptahydrate. All right? And so that is how you name a hydrate. Now, what if I took this and gently warmed it? Okay? If I gently heated this magnesium sulfate heptahydrate, what would happen if I gently heated this? Yeah, all these waters would evaporate away. Okay, and so they would all get heated and warmed out of the ionic crystal lattice. Okay, and so at that point, it would be what we call anhydrous. An anhydrous compound is a hydrate that has had the extra water removed. Well, it is a hydrate because it is an ionic compound that usually bonds with water that way. But we're going to call it anhydrous instead of hydrate. So in this case, the name of that would then be anhydrous magnesium sulfate. All right. I'm definitely working into a corner there. So anhydrous magnesium sulfate. All right. I know that that's terrible handwriting and it's way down there in the bottom right corner. But that's what we would call it then once that extra water is removed. All right. What questions do we have about that? None. Excellent. Hey, so I want to show you how to work a problem. It's actually extremely similar to our empirical formula problems about how you could figure out the amount of water present in a hydrate. all right, if you were given some information. All right, so let's just say, hey, are we good here? We got this all recorded? Almost? All right. Hey, I will put it back up on the screen in just a moment, okay? I'm saving it, but I'm going to blink it out right now. So let's say that I have a 50.0 gram sample, 50.0 gram sample of a hydrate called barium hydroxide. All right. And I know that barium hydroxide is a hydrate, but I do not know how many water molecules are trapped in the crystal structure. So I'm going to put an X in place of the number. All right. And so let's say that I have a 50.0 gram sample that contains 27.2 grams barium hydroxide. How do I know? Well, if I took the barium hydroxide hydrate and gently heated it until I drove all the water off and then massed it again, I would have 27.2 grams remaining. Okay? And so, so the first question is, what's the percent by mass? So I'll say part A. What is the percent by mass of water that is present? All right. So what I'll do for that is I'll say, hey, now here's the thing. If I had a 50 gram sample and 27.2 was barium hydroxide, how much of it was water? I'll give you a hint. Take 50 and take this away.
22.8.
All right, so about 22.8 grams of water. Hey, now remember that anytime I do a percent by mass, that is the part that I have divided by the whole. So the part of one thing divided by the whole amount. So the percent mass of water is going to be 22.8 divided by, hey, how much did the whole thing weigh?
The whole thing was 50 grams.
All right, 50.0 grams. So do that and then multiply by 100 to convert it into a percent and tell me what we get. All right, we're writing, we're working.
45.6%.
All right, so 45.6% water by mass. All right, so 45.6% water by mass. All right, so that's what they asked us for that. Now part B. So I'll switch to a different color. What color did we decide worked well besides green and yellow? We decided that red did? Okay.
I like that.
All right. And so part B says find the value of X in the hydrate. All right, so we are looking for this number right here. Now, the way that we're going to find the value of X is the first thing we need to know is how many moles of each we had present. All right, now if I have 27.2 grams of barium hydroxide I need to convert that into moles. All right, so then I'm stuck with the question, hey, how many moles is that going to be? So I need to know the molar mass of barium hydroxide. In other words, how many grams of barium hydroxide make up 1 mole of barium hydroxide. That 2 should actually be on the outside. There we go. All right. Just going to do a little work up here in the corner. What's the atomic mass of barium?
137.30.
Wow, 137. I'm just going to do whole numbers for speed here. Oxygen. Hey, notice that since I have a 2 on the outside of my hydroxide, that means I'm going to have 2 oxygens. That's going to be 32, because that's 2 times 16. And 2 hydrogens, which is 2 times 1, which is 2. All right. So then I'm going to total all that up. And let's see. That's going to be 34, 167, 171. All right, so 171 grams of barium hydroxide. So take 27.2 and divide by 171. $27.2 divided by 171. Carly, would you punch the math for me? Thank you, ma'am.
So you want me to do the one for the, you want me to divide?
I want you to do 27.2 divided by 171.
Okay.
And tell me what you get.
0.85.
So 0.15, is there another decimal number?
No.
0.159, okay. Now, let's see. So that's the number of moles of barium hydroxide that we have present. Great. Now I'm going to find the number of moles of water. Now let's see. In the water, I'm going to switch to a nice light blue color for the water. All right, now let's see, water, H2O, 2 times 1 plus 16 is 18 grams per mole. So I'm just going to say, how many grams did I have? 22.8 grams of water?
Yes.
So 22.8 divided by 18. And how much is that going to equal?
1.267.
1 decimal point 2 what?
267.
1.267. Okay. Hey, so now I'm going to write this out again. I'm going to say if I have 0.159 units of barium hydroxide, then I have 1.267 water. Divide by the lowest number. So 0.159, so I'm going to divide by 1.159 and I'll have barium hydroxide of 1. And then how many waters am I going to have if I take 1.267 and divide by 0.159? Punch the buttons. All right. 1.267 divided by 0.159. 7.999?
969.
Okay, 7.969. So that basically is 8. And so what we find out is that barium hydroxide is actually an octahydrate. Okay? And so we would name that barium hydroxide octahydrate. All right. So that is just a quick lesson on hydrates. And thank you for your time.